Welcome back to Bite-Sized Breakthroughs, where we break down cutting-edge research and explore its implications. Today, we're diving into a groundbreaking paper titled NeRF, representing scenes as neural radiance fields for view synthesis. This paper presents a novel approach to view synthesis, which is a key challenge in computer vision and graphics. Dr. Paige Turner, a leading researcher in this field, joins us to discuss this fascinating work. Paige, thank you for being here.
It's my pleasure to be here, Alex. This paper presents some really exciting advances in how we can digitally represent and manipulate 3D scenes.
Excellent. Let's start by setting the stage. Can you give our listeners a brief overview of the traditional view synthesis problem and the challenges it poses?
Certainly. View synthesis is all about generating new views of a scene from a set of existing images. Imagine you have a bunch of photos of a room taken from different angles. The goal is to create a virtual 3D model of that room that you can then look at from any angle, even angles where no actual photo was taken. This is useful for applications like 3D modeling, virtual reality, or even creating photorealistic animations.
So why is that so hard?
Well, the traditional approaches to view synthesis relied on representing the scene using either a set of 3D points connected by triangles, what we call a mesh, or a volumetric representation using a grid of voxels. These approaches have limitations. For instance, creating a high-resolution mesh or voxel grid for a complex scene can become computationally expensive and require massive amounts of storage space. Also, they can struggle to represent objects with intricate details and materials that exhibit non-Lambertian reflections, such as shiny surfaces.
That makes sense. So what's the innovation in this paper? What sets NeRF apart from these existing methods?
The key innovation in NeRF is the use of a continuous 5D representation of the scene. Instead of discretizing the scene into points or voxels, NeRF uses a neural network, specifically a multi-layer perceptron or MLP, to represent a continuous function that maps a 5D coordinate to the scene's properties. This 5D coordinate includes both the 3D location in space and the 2D viewing direction. The network outputs the volume density at that location, which tells us how opaque the scene is at that point, and the view-dependent emitted radiance, which determines the color we see from that specific viewpoint.
That's fascinating. So the network learns to represent the entire scene as a single continuous function, rather than relying on a discrete grid or mesh. This sounds incredibly efficient, but how does the network actually learn this representation? How does it take a set of images and translate them into this 5D function?
That's where the magic of differentiable volume rendering comes in. The process of rendering a view from the NeRF is fully differentiable, meaning we can calculate the gradient of the rendering with respect to the network parameters. So we train the network by minimizing the difference between the views rendered from the NeRF and the actual input images. By doing this, the network learns to represent the scene in a way that produces accurate and consistent renderings from any viewpoint.
That's a powerful approach, but I can imagine that directly training the network on the 5D coordinate space could be challenging. How did the authors address that?
You're right, Alex. The authors realized that simply feeding the 5D coordinates to the network wouldn't be enough. They introduced a technique called positional encoding that essentially expands the input space into a higher dimensional space. This helps the network represent high-frequency variations in the scene, leading to much finer details and more realistic results.
So, they're mapping the original 5D coordinates into a much larger space, making it easier for the network to learn the complex relationships between location, viewing direction, and the scene's properties. That's a clever approach.
Exactly. They use sinusoidal functions to create this higher dimensional representation, similar to what is used in the transformer architecture. This approach allows the network to capture very fine details, which was a challenge with previous methods.
Let's talk about the performance of NeRF. What are the key findings of the experiments? How did NeRF measure up to other methods? And were there any notable strengths or weaknesses?
The paper evaluated NeRF on 3 different datasets: 2 synthetic datasets featuring objects with varying degrees of complexity, and a real-world dataset with handheld captures of complex scenes. In all cases, NeRF significantly outperformed existing methods like neural volumes, scene representation networks, and local light field fusion, achieving higher PSNR and SCM scores and lower LPIPS values. This indicates that NeRF produces higher quality images that are more perceptually similar to the ground truth images.
That's quite a statement. Let's get into some specific examples. What kind of results did they see on the synthetic datasets? What about the real-world dataset?
On the synthetic datasets, NeRF demonstrated its ability to capture intricate details, even for objects with complex geometry and non-Lambertian materials. For instance, they were able to accurately render the rigging of a ship model, the gears and treads of a Lego model, and the shiny stand of a microphone. In contrast, other methods like SRN produced blurry results, and NV struggled to capture fine details like the microphone's grill or Lego's gears. Even LFF, which is specifically designed for forward-facing captures, exhibited banding artifacts and ghosting artifacts. On the real-world dataset, NeRF again showed its strength in representing fine details, as demonstrated in images of a fern, a T-Rex, and an orchid. It correctly reconstructed partially occluded regions, which other methods struggled with.
Impressive results. It seems like NeRF really excels in representing complex geometry and subtle material properties, and it's able to handle real-world images well. But you mentioned some limitations in the paper. Can you elaborate on those?
Of course. One significant limitation is the computational cost. Training NeRF requires significant time and resources. It can take 1 to 2 days on a single NVIDIA V100 GPU to train a model for a single scene. While this is comparable to other single-scene methods, it's a significant barrier to wider adoption. Also, rendering new views from the trained NeRF still requires a fair number of network queries, which can impact rendering speed, especially for real-time applications.
So while NeRF is very good at producing high-quality renderings, it's not yet practical for real-time applications. That's a key area for future development. Are there any other limitations or areas for improvement?
Absolutely. Another important limitation is the lack of interpretability. Because NeRF encodes the scene within the weights of a neural network, it can be challenging to understand how the network is making decisions and to identify potential failure modes. This makes it difficult to reason about the quality of the renderings and to identify specific areas where the network might be struggling. Researchers are working on developing techniques to improve the interpretability of these neural scene representations.
Those are important points to consider. It seems like we're at the beginning of a new era of view synthesis with these neural scene representations. Professor Wid Spectrum, a leading expert in computer graphics, joins us to offer some broader context and insights into this research. Wid, thank you for joining us. What are your thoughts on the implications of this work? How significant is this research, and where do you see it fitting in the bigger picture?
This paper is a significant step forward in 3D scene representation. NeRF's ability to capture complex geometry and materials with high fidelity using a continuous, learned representation is incredibly exciting. It surpasses the limitations of traditional methods based on discretized representations. This has the potential to fundamentally change how we create and interact with virtual environments.
It's interesting to see how this work builds upon earlier research on implicit surface representations and volumetric rendering. Do you think NeRF could eventually become the standard way to represent 3D scenes? Or do you see it as a specialized tool with limitations?
It's too early to say for sure whether NeRF will become the dominant method for representing 3D scenes. It still has some limitations, particularly in terms of computational cost and interpretability. However, its potential is vast. Imagine being able to create photorealistic 3D models of entire cities from a collection of street-level images, or to generate highly immersive virtual reality environments directly from real-world photographs. That's the kind of impact NeRF has the potential to have.
That's a compelling vision, Wad. Paige, any closing thoughts on where this research might lead in the future?
I'm excited to see how NeRF evolves. Research is already focusing on improving rendering efficiency and exploring applications beyond view synthesis, such as light field capture, depth estimation, and material estimation. Furthermore, the ability to represent dynamic scenes with moving objects and changing lighting would be a significant advancement. This paper marks a major step forward, and I believe it will have a profound impact on how we create and experience 3D content.
Thank you both for this insightful conversation. It's clear that NeRF represents a significant breakthrough in the field of view synthesis, with the potential to revolutionize how we create and interact with 3D content. We'll be closely following the progress in this area. Until next time, keep exploring the world of bite-sized breakthroughs.